Hello. Now this is not a question video as such as you can tell. This working on the board behind me is just because I was halfway through recording a past paper video and I thought, why haven't I mentioned this? Now, as I say, it's not to do with what's on the board behind me, that's just to confuse you, okay? Or myself when I'm editing a video to select the clip. So anyway, as you can tell by the title of this video, it's about the mass of products and the mass of the actual nucleus. Okay, now obviously the topic here being covered is binding energy. Now, you all know to break anything apart, we have to put energy into it. So if you want to break apart a chocolate sweetie, you have to snap it in half. Now, obviously, unless you're just a fat sod and just eat everything straight away, but yeah, so it comes from the equation, okay, Einstein's equation of E equals mc squared. Okay, now a lot of people just say that, not know what it means. Okay, now if we're going to change the mass of something, okay, therefore we have to put, if we're going to change the energy of something, if we're going to have to put energy into something, okay, we need to therefore change energy, and according to this equation, well, c is the speed of light, so it's a constant, so it's the delta m. It's the mass that changes, okay? So therefore, if we're going to put energy into if we need to change the mass of something and break it up into its components, we're going to need to put energy into it. That's kind of what that says, if you can see the theory of that. Now, one of the main problems that people get with binding energy is, well, it's all very good, okay, you have to put energy into something to break it up. But the key application of this in papers, okay, is knowing that there is a difference between the mass of the products. So what I mean by that is the mass of the product. So if you've got a nucleus and you break it up into, if you work out the individual mass of all of the protons and add that to the total mass of all of the neutrons, it should therefore roundabout equal the mass of the actual nucleus, okay? Because remember, we're not considering electrons in a nucleus, it's just protons and neutrons. We're not considering the outside electrons, we're just considering the nucleus itself, okay? So that's why I said protons and neutrons, not electrons as well, okay? So anyway, gloss over that. So the mass of the products is different to the mass of the nucleus, okay? Now, which one is more? Okay, well, it's the mass of the products, and the way to explain this, okay, is the fact that to break something up, as I said, you have to put energy into it. Now, according to this equation, E equals mc squared, okay, if we put energy into something, the thing we have to change, therefore, is the mass, okay? Or if we want to change the mass of it, when I say this changing mass, what I mean is, we're looking at the individual masses of the protons and neutrons, okay? So we're working out twice, okay? That's an overall concept. Okay, so hopefully that makes sense. If it doesn't, I'll explain it again. So if we put energy into something, if we change the energy, therefore we have to be changing the mass. So we're breaking it up into its products. So therefore, as I say, if we put energy into something, that lost energy, okay, has to be made up. I'm going to explain this very well. So it was very good in my head. Sorry. So imagine we've got a Imagine we've got a nucleus, and you want to break that up into its protons and neutrons. You have to put energy into it, okay? And that energy has to be accounted for at some point at the end, because as we know, conservation of energy means we can't lose or create any energy. So therefore, if it's split up into its protons and neutrons, okay, we've put extra energy into it. So therefore, something else must have increased as well. So therefore, the mass must have increased because according to E equals mc squared, C is a constant, so therefore the mass must have increased as well. So therefore, the mass of the products is greater than the mass of the nucleus. Okay, and this helps you to understand which way you get it round. Okay, when you're using figures, the mass of the product should always be greater than the combined. So the combined mass of the products should be greater than the mass of the nucleus. Okay, so hopefully that makes sense. And now, as I said, I'm not going to do a example of this because it's purely a knowledge video, but there are many past papers that require you to use this understanding, and most of them will have to remember a mass of a nucleus is often given to you, okay, but the mass of the products isn't. So what you need to do to work this out, okay, the mass of the products, I'm not going to go through an example, just give you a knowledge basis. So say we've got in a typical, I don't know, a typical atom, nucleus, or whatever, nucleus, sorry, we've got 141 neutrons and 92 protons. Now I'm just going off an equation I did from uranium, so that actually is uranium-233, I think. Okay, so how would you go about working out the mass of the products of this? Well, you wouldn't just work out, you could either work out the mass of the neutrons and then the mass of the protons, okay? But a way to do it is in the actual equation, okay? We've got, if you look on the formula sheet, okay, you've got also the mass, the atomic unit of mass, U, which is the mass of the proton, okay, compared to whatever you're looking at. So what you do therefore is you look in the formula sheet, and the atomic mass of a proton is 1.00728 U. Okay, so you would times that by 92, and then the neutron rest mass is 1.00867 U. So you would times it by 141, add them two together, get that as total as U, which is I think is 234, and then in a particular equation, you might be told the actual mass of the nucleus, okay, which is I think is I've got it here. Sorry, this is, by the way, this is June 2011, but I'm just using the data from the paper. I'm not answering the question. And the mass of the nucleus is 232.986 or whatever it is. Okay, so therefore these are both in U, so you would either need to convert them to kilograms or whatever it is. Okay, so therefore we've got a change in the mass there. So what you would do is use your delta E is equal to mc delta mc squared. Well, obviously there's a change in mass here. Remember, this is the mass of the products, and it is greater than the mass of the nucleus. So if this isn't greater number than the mass of the nucleus, you've done something wrong. This is the change in mass, so therefore that's the change in energy. When you put this change in mass into E equals mc squared, therefore you will get the binding energy. So that's just a quick overview of how to calculate the binding energy. Okay, hopefully it's helped you, and just a very quick analysis there. So sorry for going too fast, but it's a very, very quick little thing I wanted to go over with you. Okay, so thanks for watching. We'll see you in the next video.